I see that a lot of people have joined our training, so thanks a lot for joining this training. And today I'm gonna talk about a pre-stressed girder bridge analysis in Midas FEA. And on your screen now is the model that I'm going to create. So you can see that it's a 150 feet long girder, and it's a box girder. Let me show you the cross section. This is how the cross section looks like. You can see that it's a full cell girder, and the pre-stressing has been done both in the longitudinal direction as well as the transverse direction. So in the longitudinal direction, this is how the pre-stressing has been done. You can see the tendons in the longitudinal direction, and they pre-stress the girder in the longitudinal direction. And we have also provided pre-stressing in the transverse direction. So if you see the top view, you see certain lines on the screen which are running from top towards bottom of the screen. They are representing the tendons in the transverse direction. So basically in this training session, I'm going to talk about how you can create such a model in Midas FEA, and how you can pre-stress it both longitudinally as well as in the transverse direction. And then we will talk about how we can obtain the results from Midas FEA. So let me get started with the training. First of all, I'm gonna open a new model in front of you, and we will start with the Midas FEA training. So on your screen now is a blank model in Midas FEA, and here in this particular model I have imported the cross-section profile from AutoCAD. Since you guys must be having the drawings from AutoCAD regarding the cross sections, you can import them directly in Midas FEA using the import feature. So here you can see you can import the 2D as well as 3D from AutoCAD. So once you go to File, Import, you have the option to import 2D as well as 3D in Midas FEA. But let's say you do not have the cross-sectional drawings with you in AutoCAD. So you can still create the cross-section in Midas FEA. Now let me talk about how you can create the cross-sections and other stuff in Midas FEA. So first of all, when you will open Midas FEA, you will see on the top you have the menu bar. Then on the left-hand side, you have the work tree. It is pretty much like the interface of Midas Civil, and you guys are working with Midas Civil, so I can assume that you already know about what these functions do. So now let us talk about features that are specific to Midas FEA. So once you right-click on the model view, you can toggle grid on, and this is how the grid would look like. So this grid facilitates the creation of anything in 2 dimensions in Midas FEA. So once you see the grid, you will see that on the grid you have the X, Y directions, and these X, Y, Z directions, which are at the center of the model view, are different from the directions at the bottom right. So the directions at the bottom right, they represent the global coordinate system, and the coordinate system on the work plane, they represent the coordinate system which is local to the work plane. So right now you can see that the XY plane is the global XY plane, but if I move the work plane around, you will see that this XY plane will change. So now let me show you how you can change this work plane. If you want to change the work plane, you can go to Geometry, Work Plane, and you can go to Move, and you can move the work plane anywhere. So let's say you have already created a solid block and you want to make perforations inside it. You can move the work plane along that solid plane. You can select the reference face of the solid plane to create those perforations. You can move the work plane around. And if you want to move the work plane about any random, you can put 3 points, and Midas FEA will automatically change the work plane from the origin to that particular location. So here I am selecting the reference face to be one of the datum planes, and once I click on OK, you will see that the work plane will move. So here let me show you how you can do that. So I selected the datum face. Once I click on OK, you will see that the work plane has now moved, and still the XY coordinate are local to the work plane. So this is how the work plane has been moved. Now let's say you want to create a cross section in Midas FEA with this work plane. So you got to go to Geometry, Curve, Create on Work Plane, and then you can create anything on the work plane. So it's going to be a 2D drawing. So let's say I selected the polyline option here, and here I can create any cross section that I want. So this way you can create the cross sections. If you don't have the DXF file, you can create the cross sections in this manner, and it would be pretty convenient to work with the Midas FEA work plane when you are working on 3D models. Now let's say you want to create a line which is in 3D, which you cannot create in any of the work plane. So for that you will go to Geometry Curve 3D option, and here you can punch in the 3D coordinates of the line or any polyline you want to create, and this way you can create the lines in 3D. So this is about how you can create different 2D shapes in Midas FEA in a work plane or in 3D. So basically you gotta go to Geometry Curve, and there you have two options: create on work plane or create 3D, and this way you can create different curves, cross sections, shapes, etc. Now let me show you with respect to this particular bridge how we will do the modeling. So as I mentioned earlier, I have already imported a cross section from AutoCAD, and now I would like to work with this cross section to create the whole bridge. So right now if you tap the mouse on the top of any edge here, you will see that all these edges are individual edges, and they are not right now we cannot use these edges to create the final profile of the bridge. So first step would be to create the wire. To create the wire, I'll go to Geometry, Curve, and the Make Wire option here. So once I go to Make Wire option, I can select the individual lines or edges that I have to create a wire out of these individual lines. So you will see that I have selected the outer periphery of this cross section, and I will create a wire out of those. So once I select them, I'll click on Apply, and you will see that the color changes from black to blue, which represent that the wire has been created. Similarly, I'm going to create the wire for ducts. So I selected individual edges, and I can click on Apply, and the wires will be created. The basic idea behind creating these wires is that so that I can create the duct or the outer periphery of the cross sections in one go. So right now here you can see that now we have created the wires for the whole cross section. Now I'm going to use the extrude feature to extrude this particular wire and to create the solid out of it. For that, I'm going to go to Geometry, Generator Feature, Extrude. So basically this extrude features work in the same lines as it does in Midas Civil, and since you guys already are using Midas Civil, it would be easier for you to understand. And basically it's the same concept as that of AutoCAD. So here when you will click on Select Extrusion Profile, it will ask you to select the profile that you would want to extrude. Here in the selection pane, you will see that right now we have the face selected, and whatever face that you have in your model, you can select those. But right now we do not have any face in our model, so we will select the wire. So here you can see the wire will be selected in one go, and the outer periphery of the cross section is selected. Similarly, I'm going to select the inner ducts as well, and I'm going to create the solid 150 feet long. So I'm going to put the length as 150. I'm going to select the direction as the x-axis, and I'm going to name it as girder. And before you actually do it, you can click on the preview button here. This preview button will help you in seeing whatever you are doing beforehand. So before I actually do it, I can click on preview, and it shows me that this is how it will be created. And once I click on OK, you will see that the whole solid has been created. Now let me increase the transparency of the solid, and let me tell you how the solid looks like. For increasing the transparency of the solid, all you gotta do is select the solid, whatever solid you want to select for changing the transparency. Right now I want to change the transparency of all the solids, so I'm going to select all the solids. I'm going to right click on the solid top, then I'm going to click on transparency, and here I will select the transparency of my choice. So this is how you can see that right now we have many solids, and basically there are no ducts inside this solid. If you see the works tree here, you will see that there are 5 individual solids. Now we are going to use the Boolean operation, and with the help of this Boolean operation, we will remove the ducts from the outer periphery of the solid. For that, we will go to Geometry, Boolean operation, Cut. We will select the Boolean master as the outer periphery of the solid, and the tools would be the ducts. So this way I am selecting the outer periphery and the inner ducts, and once I do this exercise, once I select them all, I can hit on OK, and you will see that now the solid has duct inside it. So basically we have created the box girder by following this approach. So let me recapitulate what we did so far. We created the cross section, we imported the cross section from AutoCAD, then we created the wires out of the cross section, we extruded the cross section to create the solid, and then we deleted the ducts from inside the solid by using the Boolean operation. And let me again increase the transparency of this particular solid, and this is how it looks like. So this way you have completed the modeling of the solid in Midas FEA. Now let me show you the cross-sectional profile. This is how it looks like. Now we would like to create the tendons inside the solids. For creating the tendon, we have 2 options in Midas FEA. I'm going to use both of them so that you learn how you can create curves in Midas FEA. So when you go to Geometry, you have the curve option. You can go to Create 3D, and here we have the tendon profile option in Midas FEA. So with the help of this option, you can uniquely create the tendon profile, and it is similar to the one that we have in Midas Civil, so it would be pretty comfortable to use with. So I'm naming it as tendon 1, and here I'll put in the insertion point of the tendon. So right now I'm creating the tendon at the centroid of the cross section, not on the centroid, but at the origin, and then I will move the tendon around wherever I want to put it. So right now the tendon insertion point would be 0, 0, minus 0.2 feet, and now I'm going to create the different cross section along the profile of the tendon. At 30 feet it's going to go down, so I'm going to put Z as minus 6 feet. Then it would be a straight tendon from here on. So here I'm punching in the coordinates. You can also bring the coordinates from the Excel file. So if you have the Excel file, you can bring in the coordinates from the Excel file. So this is how I'm creating the coordinates at each location so that I can obtain a smooth tendon profile. $110, it's going to be at the bottom again, and $120, it's going to be at the bottom again, and at the end support at 150 feet it's going to go up, so Z would be equal to 0. So once you have defined this profile, you can click on preview and it will show you how the tendon will be assigned. So you can see a small green curve running from one end of the bridge to other end of the bridge. It represents how the tendon will be created, and you can also see it here. So once I see that everything is fine, I'm comfortable with how the tendon profile is created, I can hit on OK, and you will see that now the tendon profile appears in blank. So this way the curve has been created. Let me highlight the curve for you. This is how it has been created. So it's pretty easy and comfortable to create tendon profile in Midas FEA by using the tendon profile generation feature. Now I'm going to create the tendon profile at other locations by copying this particular tendon, because the tendon profile would be more or less the same along the other webs. So this time I'm going to use the transform feature, and I'm going to translate this tendon profile along the Z direction and along the transverse direction of the box girder so that I can create the tendons at other locations. So here I will select the object shape, so I'll tap on the tendon here, it will be selected. Then I'm going to select the direction. This time I'm copying it in the Z direction. So I'm going to select uniform copy here. I'm going to copy it by 0.25 feet, or you can say 3 inches, 4 number of times. And before I actually do it, this is how it will be done. So I clicked on preview, and you can see this is how the tendons would be copied. So I'll click on apply, and you can see this is how the 5 tendons have been created. Now I'm going to copy these tendons at other locations. So I selected the tendons again. The 5 tendons have been selected, and now I'm going to move them in the transverse direction. So I'm going to select the transverse direction. You can see this is the direction bar here. This line represents the direction, and I'm going to move it to minus 0.5 feet. So I'm going to move it by 6 inches in the same web. So this is how it would be moved. Let me show you the cross section again. It shows how the tendon profile will be moved. And once I hit on apply, you can see that now I have placed the tendon at the required location. Now I'm going to select these all tendon profiles, and I'm again going to copy them in the transverse direction so that I can have 2 sets of tendons in each web. All right, this is how it will be done. So right now you can see that in the center web we have 10 tendons, and these tendons are almost of the same geometry. The geometric profile is same. So I created 1 tendon, I copied it in the Z direction, and I created 4 more tendons out of it by copying it, and then I translated the whole tendons at any other location so that I have the complete set of tendon profiles. The other webs will also have the same tendon profiles, so I'm going to select them all again, and I'm going to copy them by 17 feet, which is the distance between 2 webs. I'm going to select the direction, and before I actually do it, I will see the preview. This is how the tendons will be copied. You can see the preview. I'll hit on apply, and I'll select the same tendons again. I'll select the transverse direction, and this time I'm going to copy it in the other web. So this is how it will be copied. Once I click on OK, you will see that the tendons have been copied to all the 3 webs. So it was pretty easy to do. We first created a typical tendon profile. We copied it along the Z direction and the transverse direction. So we created all the tendons that we needed in a particular web. Then we transferred the tendons from one web to the other by copying it all through. So this is how you can create the tendons in webs. Now let us talk about how you can create the tendon in the inclined webs. So for that, let me show you how you can create the tendons in the inclined web. So first of all, again, I'm going to use the tendon profile definition dialog box. So let's say I'm going to name it at tendon 2 here, T2, and I'm going to define the insertion point, and here I'm going to define the location of the tendon. The inclined web is at a distance of 33 feet from the centroid, so I'm going to define the y direction to be 33 feet, and in the same way we did for the first tendon, we are going to define for the inclined tendon. So I'm defining the coordinates. It's going to take some time, so here you can copy it from Excel if you have. 60 feet, it's going to be at minus 33. So right now I'm punching in the coordinates so that I can create the tendon profile. And once I do it, I'm going to show you how you can incline it so as to put it in the inclined web. Okay, here we go. So before I actually put it, I will see the preview. This is how it looks like. You can see on the right web, you can see the green color tendon, and it looks okay to me. So I'm gonna click on OK, and you will see that the tendon will be defined. Right now you can see that at this very location, the tendon is going outside the web. So now I'm gonna create an inclined tendon so that I can put it in the direction of the web, so that I can align it with the web. For that, I'm going to use the rotate option. So when you go to geometry transform, you have the rotate option here. So I'm going to hit on rotate. I'm going to select the object shape that has to be rotated. In this figure, we have the tendon. Then I'm going to select the revolution axis, which would be the global x-axis. So I selected it. And now I'm going to select the location at which it has to be rotated. I selected the location, and I'll rotate it by the degree of rotation of the web. So this is how it will be rotated. So as you can see here, the tendon has been rotated, and once I'm comfortable with how it has been rotated, with the angle it has been rotated, I'll click on OK, and you can see that now we have the tendon which is put inside the web. Now I'm going to do the same exercise with this particular tendon. I'm going to copy it in the Z direction and then along the transverse direction so that I can create the whole set of tendons. So first I'll go to transform, translate option. I'll select the direction of translation as a global Z direction. And this is how they will be translated. You can see the preview before you actually do it. I'll hit on apply. Then I'm going to move it in the transverse direction. So I'll select the transverse direction, and I'm going to move it by minus 0.5. This is how it would look like. So I just selected it. I'll hit on apply. And once I hit on apply, the tendons will be moved. And then I'm going to copy these tendons again. And this time I'm going to copy it in the transverse direction by 1 feet so that we have 2 sets of tendons at each web. So it's done. You can see that the inclined tendons have been created in one of the inclined webs. Now I'm going to copy these tendons to another inclined web, but if you'll copy it, they would be at, the angle of rotation wouldn't be same. So I'm going to use the mirror option. So I'll go to geometry, transform, mirror. I'm going to select these tendons, and in the mirror plane, I'm going to use one of the datum planes. And before I actually do it, I'm going to see the preview. Let me show you the cross-section view. So this is how it will be mirrored. You can see that it is now at a perfect location. And once I'm comfortable with it, I will click on OK. And you can see that now we have created the tendon profile in all the 5 webs. And you can see that the inclined tendons have also been created. So this completes the definition of the longitudinal tendon profile. Now let us talk about how we can define the transverse tendon profile. For the definition of the transverse tendon profile, I'm going to use another approach by which you can define the tendon. For that, I'm going to go to geometry, curve, create on 3D line. So basically, the idea behind creating the tendon is to have a curve. And once you create the curve, you will mesh it, and then it will be categorized as a tendon. So the tendon definition tool that we used, it was only to create a curve. So right now I'm creating one more curve here. So I'm putting in the global coordinates. So here you can see I created the transverse tendon. Let me show you how the tendon has been created. So in this view, you can see that this highlighted curve is the transverse tendon, which is on the top slab. So now I have created it at one location. It's going to be the same throughout the length of the bridge. So I'm going to copy it. So I'll go to geometry, transform, translate. I have already selected this particular tendon. I will select the direction and I will select uniform copy. I'll copy it by 5 feet, 26 number of times, and this is how the copying will be done. You can see in the green how the copy will be done, and it looks good to me, so I'll click on OK, and you will see that the transverse tendons have been defined. So this completes the geometric modeling of this particular bridge. We have a 150 feet long bridge. It's a post-tension box girder bridge. We have the tendons running in the longitudinal as well as the transverse directions. And now we would create the finite elements out of it. For creating the finite elements, we need to have the properties that we can assign to the finite elements. So now we will define the material parameters. For defining the material parameters, we will go to Analysis, we will go to Material, and we will go to Create Material here. So I'll click on Create Material, and first of all I need to define the concrete material, then I'll define the steel material. You can see that the unit system here is Newton per feet. So let me change the unit system. You can change the unit system from the bottom here. You can change it to Gibbs. So now let's go to Analysis, Material again. I'll go to Create, and I will define the material from the database. So I'll click on Database here. I will select ASTM Reinforced Concrete Database Grade C6000. So this way I've selected the material. I hit on Apply, and you can see material has been defined. It's the same thing as that of Midas Civil. Then I'm going to define a steel material for the tendon, and this way I have defined the steel material for the tendon. So this way we have two different materials, one for the girder, the other one is for the tendons. Now we will define the parameters for meshing. For defining the parameters, I'll go to Analysis, Property, and here you can see when you go to Analysis, Property, we have the Create option here. You can click on the drop down menu, and here we have different types of items that you can create. The girder will be modeled as 3D solid elements, so I'm going to go to 3D. I'll name it as girder. The material would be reinforced concrete grade C6000. I'll hit on OK, and the girder is created. Now I'm going to create the tendon. The tendon will be created under the reinforcement option, so I'll go to Reinforcement. I'll name it as tendon. I will define the tendon material, and I will punch in the cross-sectional area. I know the cross-sectional area in inches, so let me close this window, and I'll change the unit system from feet to inches. And again, I'm going to go to Property. I'll create Reinforcement. I'll name it as tendon. The material would be steel material. The tendon area is 1.83 inches, which corresponds to 12 strands. And all these parameters, the ultimate strength and the yield strength, I'm keeping it as it is. You can change the material code according to your own wish. And since it's a tendon, I selected the tendon here. So this way, I have created the tendon. Now I'm going to create one more section just to tell the program how the tendon is assigned. So I'm going to create bar section here, and you can see this is how the tendon property has been created. Okay, so this way we have created the definition of material. We have defined the tendon as well as the solid for the meshing. Now we can go ahead and mesh the entire thing. For meshing, let me change the unit from inch to feet again. And I'll go to Mesh, Auto Mesh, Solid. I will select the solid, which is for the girder, and I can ask the program for the best element size, or I can put in the element size by myself. For me, 2 feet looks good. Let me see the preview. Okay, so once you define the element size, you can click on the preview button, and it shows you how the meshing will be done. So I selected it as 2 feet. I'll name it as girder so that I can categorize it later on. This is how it will be meshed, and I'll hit on Apply, and it will take about 10 seconds to mesh the entire solid. Okay, it did it earlier. So here you can see the meshing has been complete. So this way you did the meshing for the girder. Now you cannot see the tendons inside it, so I'm going to go ahead and hide the mesh. For that you can go to mesh under the works tree, and you can hide the girder. So this way you can see the tendons again. Now let's mesh the tendon. For meshing the tendon, I'm going to the cross-sectional view so that I can clearly select the tendons. So now I'll go to mesh, auto mesh, edge. The tendon is an edge, so I'm gonna select the edge. The interval length I'm keeping as 2 feet. And here the property would be tendon. It's a reinforcement tendon property, so I'm putting it the tendon property as reinforcement. I checked on the reinforcement option here, and I'm gonna name it as tendon. After you do it, you can let's name it longitudinal tendon and select all the tendons. So here I'm selecting all the tendons that I have. All the longitudinal tendons will be selected. Here I'm selecting all the longitudinal tendons, as you can see here. And once you do this exercise, once you see the 50 edges, the 50 tendons have been selected, you can click on apply and the tendons will be meshed. So this is the process to create the tendon. Earlier you were creating the edges that are required to mesh to be created to tendons, but now you have created the tendons by meshing it. Now I'm going to create the transverse tendons, so I'm going to name the mesh to be transverse tendons, and I'm going to select the edges for the transverse tendon. So here you can see 27 tendons have been selected. I've shown you the isometric view, and you can click on apply again and the tendons will be meshed. So this way the meshing of the transverse tendons has been completed. Again, you can see in the mesh we have these many reinforcements. 27 correspond to transverse tendons and 50 correspond to longitudinal tendons. So total we have 77. So this completes the meshing. Now I'm going to click on show girder so that I can see the girder. Now we will need to define the boundary conditions. For the definition of the boundary conditions, I'm going to go to analysis, boundary condition, constraint. So I'm constraining the girder. I'm going to make it a simply supported girder. So first of all, I'll give the name to the supports. I'm going to name it as supports. And I'm going to select the nodes here where I want to apply the restraint. So at this node, I'm going to apply dx, dy, dz restraint. T1 corresponds to global x, T2 corresponds to global y, T3 corresponds to global z. So I'm going to restrain all three of them. And at the other nodes, I'm just going to restrain dz and dx, and dy would be freed so that it allows thermal expansion. I'm going to hit on apply, and this is how the supports have been applied. Now at the other end, let me go to the other end. And at this end, I'm just going to apply the dz restraint so that it can expand due to thermal loads in the x direction. So this way I'm selecting the nodes where I want to apply the supports. And once I do this exercise, I can hit on OK, and you can see that the supports are assigned. So this completes the definition of supports. Now I'm going to define the load for this particular model. I'm defining two different types of load here. One will be the body force, which will be the self-weight. The self-weight will be automatically calculated by the program. So for that, I'm going to go to analysis, load, and I'm going to go to body force. I'm going to name it as self-weight. It would be applied in the direction of gravity by -1 feet. Sorry, -1 would be the factor. If you want to apply any other factor, you can punch it here. And this way, the self-weight has been defined. Now I'm going to define the pressure load on the top of the top slab. So let me see the cross-sectional view. And for defining the wearing course load, I'm going to use the pressure load option. So I'm going to go to analysis, load, pressure load. I'm going to name it as pressure, and it's going to be on 3D elements. So I'm going to name it, I'm going to select a 3D element face, and I'm going to define what would be the pressure unit. And here I'm going to select the 3D face. So I'm going to create a rectangle on the top slab element so that all the faces would be selected. So once I define this pressure unit here, I'm going to click on OK, and you will see that the pressure load has been defined. So it's pretty easy and convenient to see the pressure load, to define the pressure load here, and you can manually check it whether it is defined right or not. And to undisplay this particular loading, I'm going to go to load in the work tree, and I'm going to hide the pressure load. If you guys have any questions, if you have any question in between the session, just type in the question, and towards the end of the session, I'm going to take up all the queries that you guys have. So please feel free to punch in any question in between the session. All right, so we have defined the self-weight, we have defined the pressure load on the top of the top slab. Now let us define the reinforcement. For defining the reinforcement, I'm going to deactivate the mesh for the girder. So I'm going to right click on it, and I'm going to click on hide, and it has been deactivated. Now let's go to the cross-sectional view again and go to analysis, load, and here we have the option pre-stress for reinforcement. So you can click on this option, and let's name it as longitudinal pre-stress. I select all the tendons which are in the longitudinal direction. So I'm selecting them one by one here. You can also select them from the work tree. So here I'm selecting all the tendons one by one. And finally, the longitudinal tendons have been selected. So this way, all the longitudinal tendons, 50 reinforcements or tendons have been selected. I'm going to apply the jacking stress. And for that, I'm going to change the stress dimensions to be Kip's-inch. I'm going to give it a post-tension stress of 170 Kips per inch square. I'm going to hit apply, and you will see that the pre-stressing load has been applied on the tendons. Now I'm going to apply the pre-stressing load onto the transverse tendons. Again, for that I'm going to go to the cross-sectional view. I'm going to name it as transverse pre-stress. So let me change the name. And here I'm going to select the tendons which represent the transverse tendons. So this way they are selected. And then I'm going to click on the stress again. And let me show you how you can select the tendons from the work tree. So here I'm going to the work tree, and here the tendons with name transverse tendons will be selected. So I'm selecting all the transverse tendons from the work tree. So if you want to select it from the work tree, go ahead and go to the work tree and select it from the work tree. If you want to select it from the model view, you can do that. So for the transverse tendons, the stress is 150 Kips per inch square, and this way the pre-stressing has been done in the transverse direction. So here you can see how the pre-stressing force is applied by Midas FEA in longitudinal and the transverse direction, and this completes the entire modeling for this thing. Now we can go ahead and define the analysis cases that we want to analyze. For that, we will go to analysis, analysis case. We will click on that. We will first apply dead load. We will activate all the mesh elements, including the tendons and the girder. We will activate the supports, and we will activate the self-weight, the pressure, the longitudinal pre-stress, and the transverse pre-stress, everything into it. And here on the bottom left, we have an option to solve each load set as independent load case. So I'm going to click on this, and all these 4 load cases, we can see the results individually. So once I click on OK, you can see that load has been defined. Let us define one more analysis case for the transverse tendon. So I'm going to name it as trans. And again, I'm going to activating all the tendons. And I'm going to activate the supports and only transverse pre-stressing will be activated in this case. So this way we have two analysis case. Everything has been done. Everything is complete. So I can go ahead and go to analysis solve, and we can solve the model to obtain the results. Now let me take up some questions from you guys. Then we will talk about how we can obtain the results from Midas FEA. Okay, I've got a couple of questions from a couple of people here. Mr. Rao has asked a question. Only one tendon area was entered. Can we, for transverse as well as longitudinal tendons, can we define the different areas for different types of tendons? Yes, you can define any number of tendon areas. You can define different properties for longitudinal as well as transverse tendons. So depending on whatever parameters your tendon has, you can define different tendon properties for longitudinal tendons or transverse tendons or inclined tendons or half tendons. So there is no limitation. You can define as many tendon profiles or as many tendon properties as you want. There is one question by Mr. Ramin. The question is, why the second load case? What for? Generally, we do not require the transverse load case because the first load case would have the transverse results into it. So we don't need it, but I was just telling you that you can define more than one analysis case in Midas FEA, and you can analyze them individually to obtain the results. If you guys have any more question on the modeling aspect of the training we did today, you can ask me now. Otherwise, I'll go ahead and show you the results. So I'll wait for a couple of minutes and then I'll show you the results. If you have any question regarding the modeling aspect in Midas FEA, do let me know now. Otherwise, I'll go ahead and do the results thing. Okay, there's a question by Ramin. The question is, why two different material definitions for tendon? For tendons, we only have one material. So if I go to materials here, you can see that there is only one type of steel material which I have used for tendon. But if the tendon have different types of materials, or if the tendon has different area, you can define multiple materials. That is okay. So I have only defined one material for tendon. Again, if you have any more questions, please feel free to ask any question. This session is only for you guys, so you have all the right to ask any question you want. Seems like we do not have any questions at this point of time. So let me go ahead and let me show you the results for this particular model. So I have already analyzed a model here, and let me share the results of this particular model with you. It's the same model. I did it earlier. I analyzed it. It took about 2 minutes to do an analysis. So here it is, the model. After you perform the analysis, you can go to postworks and you can see the results in this postworks. So for the self weight, you have these many results. You can go to results, reactions, displacements, 3D strains or stresses, or 1D reinforcement stresses or strains. So let me show you how deformations look like. So I double clicked on the deformation. This is how the deformation profile looks like. If you want to obtain the deformation at individual location, you can check on the mesh here. So when I go to post style, I can check on the mesh edge. This is how the mesh edge would look like. And then I'm going to go to post probe result, and I can tap on any node and it's going to create a tag on it so that I can obtain what is the deformation at individual location. So here you can see this is how the deformation has been obtained. So go to probe result and it's going to give you the liberty to select any node, and you can get the value for the result that you want to obtain. Similarly, if you want to obtain the stresses, let me show you how the stresses would look like. So I'll go to 3D stresses. So this is the stress profile of the cross section. Let me uncheck the mesh edge. This is how the stress profile looks like. Let us see the stress profile at the center of the cross section, at the center of the bridge. For that, I'm going to go to post style, and I'm going to go to the clipping plane option here, and let me hide all the curves that I have here. Okay. So when I go to the clipping plane option, I can go to define, and here it is. This is how you can define the clipping plane at different locations. And once it is defined, you can see how the stresses look like. These are the tendons that are coming out of the cross section. If you want to hide them, you can also hide them. And if you want to now obtain the stress at any location, check on the mesh edge and go to probe result feature, and you can tap on any node to obtain the stress value. So this is how the stress is obtained. You can see the compression and the tension stress here. Again, for any location, you can go to probe result feature. Similarly, you can obtain stresses in different directions. This is how the stress appears in local y direction, etc. If you want to obtain the stresses in the tendons, go to 1D stresses. So let me show you how you can obtain the results for stresses. So here I have the pre-stressing load case, in which I have done the pre-stressing in both longitudinal and transverse direction. I'll go to 1D axial stresses. So once I double click on it, you can see how the stresses are obtained. And let me hide the girder mesh for you so that you can see the stresses easily. So I have hidden the girder, and this is how the stresses appear on the longitudinal as well as the transverse tendons. Okay, let us see the deformation profile for the pre-stressing. This is how it looks like. This is a very scaled deformation. You can change the scale from here. So this is how the deformation appears. If you just want to see how the displacement would look like from the transverse tendons, this is how it looks like. So that is all about 3D stresses, strains, etc. that you can obtain from Midas FEA. But how about the results that you need for design? Moments at individual cross sections, shear forces, etc. So for that, we have the local direction force sum option here. So in the post window, we have the local direction force sum, where you can select any plane in the model view, and it will give you the results in that particular direction, in that particular plane. So for that very purpose, I have defined several surfaces or planes. So this is how I've defined it. I have defined the different surfaces at 10 feet apart, so that I can obtain the bending moment and shear force and stresses, etc. at 10 feet locations. So for that, again, I'm going to go to post. I'm going to go to local direction force sum, and it will ask me to create the plane where I want to obtain the results. So I'll click on add, and since we have the solid elements here, I will select the element type as solid, and in the 3-point option, I'm going to select the 3 points on the plane. So here it is. Let me select the 2nd point and the 3rd point. So once you select this plane, Midas Civil will give you what is the moment, Midas FEA will give you what is the moment, shear force, etc. So let's name it as 40 feet, and click on 40 feet here. You can either plot it or you can click on table, and it will do the summation of the different solid elements which it is crossing, and it will give you the bending moment diagram, the shear force diagram, the stresses, etc. So here it is. You can see on your screen now that we have obtained the force X, which is force in the X direction, axial force Y, and other values. Let me change the units to Gibbs feet so that you can. So right now I'm changing the units, and since it involves a lot of calculations, it's going to change the units from Gibbs feet to Gibbs inches. And once I do it, you can see that the moment have appeared in Gibbs feet unit. So it's not about only analyzing finite elements. If you want to obtain the design forces from Midas FEA, you can create the planes at different locations, and you can go to local direction force sum, and you can obtain the items that you need for the items that you need for design as per the code. The code asks you to calculate the moment of resistance. It asks you to calculate the shear force, etc. at different locations, and then you can obtain the moment of resistance, and you can compare it with the design bending moment, shear force diagram, etc. And this way you can check everything. So this completes the training for today. If you guys have any questions regarding any item, anything that we did today, please feel free to ask me any question, and I'll be more than happy to answer any of your question in the real time. Okay, I have a question from Ramin. The question is, would this type of boundary condition surface suffice for this complicated 3D model? Is it possible to have linear and surface boundary condition feature? Yes, we do have these kind of features too. Let me show you how you can define the support as per surface or linear, etc. So let me change the analysis to pre-mode. So when you go to analysis, boundary condition, constraint. So in constraint, you can select either surface, you can select either node, you can select curve, etc. And then you can specify the boundary condition based on the geometry that you have. So this way you can specify the support on these things. If you have any other questions, let me know the questions and I'll answer the questions. Okay, I have one more question from Ramin here. The question is, can you please show us how to obtain net forces in the tendons after loading? So as you can see here, let me show you how you can obtain the forces in the tendons. So in the post works, you can see that we give the stresses and strains for the tendons, and with the help of these, you can obtain the forces inside the tendon. Or if you want to obtain what is the stress inside the girder due to tendons, you can go to 3D stresses and you can obtain the stress. So this is the stress in the girder due to the tendons. There's one more question by Mr. Rao. The question is there any design feature option to optimize the tendons, number of profile based on dead load and live load demands? We do not have any such automized feature that would automatically change the number of tendons or optimize the number of tendons or profile based on dead load and live load demands. So I'm afraid, Mr. Rao, we do not have any such function. There is a question for moving load analysis. Can you perform moving load analysis in Midas FEA? Yes, Midas FEA can be used to perform moving load analysis. The moving load analysis features are more or less same as that of Midas Civil. Let me show you how you can define the moving load data in Midas FEA. It's pretty simple and convenient, and every time you can either do the influenced line approach or the influenced surface approach. So when you go to load, here you can see you have the moving load analysis option, and this way you can perform moving load analysis in Midas FEA. So here you can see moving load analysis can be done in Midas FEA pretty easily. Again, if you guys have any questions, I'm here to answer your questions. Please let me know. Okay, there's one more question by Mr. Ramin. The question is, any crack propagation feature in Midas FEA? Yes, Midas FEA does provide crack propagation feature. And if you go to the material definition, here you can see that under the material, you can define the total strain crack material. And once you perform nonlinear analysis, you can obtain the crack propagation in Midas FEA. So Midas FEA can surely do crack propagation analysis. There is one more question by Mr. Rao. The question is, can you get forced resultants for individual webs? Yes, you can obtain the forced resultants for individual webs. For that, you got to select when you go to the local detection force sum, you will select only the solids which are representing that particular web, and this way you can obtain the results for individual webs. So you can obtain results for individual webs in Midas FEA. That shouldn't be a problem. So I would like to thank you all for being in the training.